Hello, good morning, sir.
Yeah, good morning.
Welcome, sir. Welcome.
Yeah.
Sir, if you are conversant, can we start, sir?
Yeah, just a minute. Let me. Yeah, you
Okay,
can
not an
start.
issue.
I think.
Okay, sir. Then we'll start the introduction, sir.
Yeah.
Thank you, sir.
Good morning to one and all. Today is the last day of the FDP. Hope you have enjoyed the last 4 days session. Today in the first session, we have Dr. Sandeep Chaudhary sir, who is professor at Department of Civil Engineering, IIT Indore. Will talk on one of the interesting topics on microstructure of concrete. His areas of specialization are structure analysis and design and building materials, including waste utilization. Sir has received bachelor's degree from MBM Engineering College, Jodhpur with honors in 1996, master degree from Malavia Regional Engineering College, Jaipur with honors in 1999, PhD from IIT Delhi in 2006, and postdoctoral research fellow during August 2010 to July 2011 from National Research Foundation, South Korea. He has a total of 26 years of teaching experience. Sir has offered a research fellowship by the Hong Kong Polytechnic University for 2 months in 2017. Sir has QIP fellowship for pursuing PhD at IIT Delhi by MHRD Government of India from 2002 to 5. Sir has achieved the many academic positions held in his career from lecturer to professor. He has vast research experience in structural engineering, sustainable construction practices, composite bridge, novel brick and block, microstructure and durability of concrete, advanced characterization techniques, waste management and building construction materials. Without taking a lot of time, I would like to welcome once again Sandeep Chaudhary sir. Now I request to sir to start the session. Thank you.
Yeah, thank you for the introduction. Let me share. Okay. Yeah, I hope the screen is visible now.
Yes, sir, it is perfectly visible, sir.
Yeah, okay. So we'll be discussing little bit about microstructure of the concrete today. And if you look into the history of concrete, and particularly in perspective of research which has been carried out on concrete, then people used to work on the strength aspects some time back, and the compressive strength, flexural strength, impact resistance, they were the some standard tests which were used to define or which were used to ascertain the quality of concrete. Over the years, people realized that just the strength aspects are not important, but along with that, the durability aspects are also equally important. So people started focusing on the durability, and we know that this Indian Standard 456 code, it was revised in 2000, and there's a major change in this code in the sense that the code emphasized on the durability equally as it was emphasizing on the strength in the earlier version. People realized the importance of the durability, and then they worked on the different aspects of the durability. Like for strength, people used to do compressive strength tests, flexural strength tests, etc. For durability, people started doing permeability tests, shrinkage tests, corrosion tests, carbonation tests, freeze and thaw tests, so on and so forth. But actually, it was realized later on that these tests and these results, whatever we are observing the results are manifestation of something else. And until unless we do understand the real behavior, or we do understand the real cause of that behavior, then it will be just half story. So people started looking deep down into the concrete at the level of microstructure, and they realized that yes, this strength properties or durability properties and other type of properties which people were investigating, that they are manifestation of this microstructure of concrete. And it's very important to understand the microstructure of the concrete if we really want to decipher what's happening inside the concrete. Before going to that, let's understand even the cement chemistry. Like we know that in concrete, typically we do have cement and we do have coarse aggregate, fine aggregate, water, and sometimes admixture, which includes superplasticizer also. So if you see a typical chemical composition of cement, then there's a sort of halite there in the cement, belite there. Halite, of course, you might be knowing mostly it is the mineral which is responsible for early age strength gain. However, it leads to greater reactions at early age, and thermal means increase of temperature is a problem due to that. Anyway, C3S is a major component of cement. Then C2S is another major component of cement, which is responsible for the late strength gain. Then C3 aluminate also, which is responsible for early setting of the cement. C4AF ferrite is there. CS gypsum is there. Gypsum is used to reduce the setting time, to increase the setting time. And then Portlandite. So many type of minerals that are present in the cement. So it's not just that one type of mineral is present in the cement. Let's see what happens when it reacts with the water and what happens in the hydration of the cement. So when there's a hydration of the cement, there's a complex chemistry which is involved. You can see here a lot of equations. We need not go into much detail into those equations because that's not our domain as on today in this lecture particularly. But what we can understand from this slide is that it's not that simple, which we do understand. There are large amount of reactions which are taking place in the cement. And these reactions, basically, they are responsible for the strength which we are observing, or they are responsible for the durability properties which we are observing. So we should be very cautious about like the presence, how much C3S is present, how much C2S is present, how much halite is there, how much belite is there, how much ferrite is there, how much gypsum is there, because they will participate in this chemical reactions that will ultimately, and on the surface or by naked eyes we'll be able to see, and by those tests we'll be just able to see the compressive strength, flexural strength, or some durability properties. So this cement chemistry has a very important role on the durability actually, and it helps in understanding the behavior of the cement first. So we need to know the cement chemistry very clearly, because only then we can understand the behavior of the cement. Then the durability characteristics like carbonation, acidic, and chlorination, etc. They depend on the free lime present after cement hydration. So again, if we know the cement chemistry, only then we'll be able to judge the amount of free lime which is present after the cement hydration. So that again is quite important for understanding the durability, etc. Also, like as we say that like one of the most important strength parameters which defines the strength of concrete is the compressive strength. Similarly, one parameter which defines the strength of which defines the durability of concrete is permeability, or is permeability. So water penetration depth is also related somehow to permeability. So the water penetration depth also depends on the pores which are formed from the volume reduction. And of course, this volume reduction is a function of the cement chemistry or hydration reactions, which are a function of cement chemistry. Similarly, alkali-silica reaction, again another durability-related problem, and which is quite detrimental sometimes for the concrete in long run. So alkali-silica reaction, sulfate attack, effect of seawater and other environmental threats, they can be better understood by cement chemistry. Now this cement chemistry, if we need to understand in turn, we need to go to the microstructure analysis. Let's see what this microstructure analysis is all about. Now there are different forms of microstructure analysis. Analysis at the microstructure level can be basically done in two phases. One is sort of conventional microstructure analysis, where we do sort of imaging, etc. Another is chemical analysis. So in the conventional microstructure analysis, we identify the mineral arrangements under microscope. That is, we do observe the concrete under the microscope, and then we try to find out that which types of mineral are present there. So it's sort of taking a photograph at a high magnification level, and then seeing that image, and out of that image, then identifying like which type of mineral is present. Now, this microstructure analysis can be studied using scanning electron microscope, optical microscope, TEM, etc. Other side, if we go to the chemical analysis, then in chemical analysis, basically we identify the types of minerals which are formed in the concrete. And this chemical analysis can be done using EDS, XRD, spectroscopy, etc. So both are very important. We need to go to the microstructure analysis also, and we need to understand the chemical analysis also. Now let's see this microstructure analysis through these microscopes, etc. So it is showing this slide is showing the concrete under different magnification and where we can see the mineral arrangements. So this is how the concrete will look like if we are seeing it from the sort of naked eyes. But if we zoom it out at 200x, that is if we magnify, if we use magnifying glass of 200 times capacity, then a glass which will magnify everything by 200 times, then this concrete which is looking like this, it will look something like this. If further zoom in a selected portion, then that will look like this at 2000x. If further zoom at 5000x level, then we'll see the concrete like this. So you can see the concrete is same, and but if we keep on zooming out at different magnification levels, then the type of arrangement, mineral arrangement, which we see is quite different, distinctly different. And so the idea is that if we are just going through the naked eye and just visualization by the naked eye, we'll never be able to see all these aspects, that all these different phases which are present in the concrete. And of course, each of these phases has a certain role in the strength development as well as in the durability related issues of the concrete. On the other hand, if we do the chemical analysis, then here we identify the minerals. Like typically, this is a sort of a typical concrete matrix, and you can see this comprises of calcium hydrates, then calcium silicate hydrates, ettringites, calcium alumina silicate hydrates, ettringite, and calcium silicate hydrates, CSH gel. Of course, CSH gel is the one which we ideally look for after the complete cement hydration. Ideally, a cement will be better if the CSH gel is more and more there, and it is worse if the ettringite is more. So if we compare all these three, then this is the priority number 1 to us, and this is priority number 2, and this is of course not under our priority. So we can compare like this. So if you have two images, we can see the image which will have images of two types of concretes at certain magnification level. Then when we can say that if one image is having more contribution or more participation of CSH, then we'll say that that concrete is better. This is a typical microstructure image here. You can see here, these are the aggregates, quartz aggregate, which are present there. This is the cement paste, which is visible here. Magnification level is, you can see that this denotes just 200 micrometer. And of course, this is cement paste, this is cement paste, and this is the transition zone between aggregate and the cement paste. Now, this transition zone is very important. Normally, we do think that the strength of the concrete is governed by the aggregates or it is governed by the cement. So it will be not conventionally or normally people think that a concrete is going to fail when either the, yeah, please. Any doubt? I think somebody is not on mute. So conventionally we think like if the concrete is going to fail, then conventionally we think that either the cement paste is getting failed or the aggregate is getting failed. But actually it doesn't happen. Actually the weakest part of this microstructure is the interfacial transition zone. And we need to look for that interfacial transition zone. We need to look for the failure of that interfacial transition zone, because it is the weakest part. It will be the part that will fail first, and it's quite complex phase here because it's a zone which is lying in between the aggregate as well as the cement paste. If you see typical hydrated cement paste, and this is another microscopic image, and you can see the magnification level. This is just denoting 1 micrometer only. So a huge magnification level. You will see three types of structures. One is this A, plate-like structures. So basically they are sort of crystals or platey structures. They contribute about 20 to 25% of the solid volume, and they are calcium hydroxide crystals basically. Another is like you are seeing a lot of this B portion, cloudy type of structure, and this is actually calcium silicate hydrate, and this forms 50 to 60% of solid volume in hydrated cement paste. And typically, as we have discussed, our priority is there should be maximum calcium silicate hydrate, then calcium hydroxide, and the remainder is occupied by calcium sulfoaluminate hydrates, ettringite, etc. Like these needle type of structures. So they are basically ettringite type of structures, and they are the least preferred because they cause certain durability related problems in time. So ideally, we should ensure that there should be more and more such type of structures in the microstructure, because this is the calcium silicate hydrate, which is the hydrated cement paste, and this gives a confidence also that yes, hydration has taken place completely for the cement paste. Now we can easily identify the incompletely hydrated cement particles also in this microstructure of the concrete. They can be easily identified by their characteristic brightness in the image. So you can see here there is a characteristic brightness in the image, and from their morphology in secondary electron mode, they also have a tendency to attract each other. And what they do is they form, because once they attract each other, then they form flocks, and which these flocks in turn they can entrap a large amount of mixing water. The undesirable variation in local water cement ratio therefore happens, because the thing is, once these flocks are there, they are going to attract large amount of mixing water, then other side the water will be less. So there is now unbalance of the water in the concrete matrix. And so what is the takeaway from this slide is that if you are seeing some microstructure image of a concrete sample, and if you are seeing certain characteristic bright images there, then you should be very cautious. That is telling us that these bright images are basically telling us that yes, the hydration has not taken place completely, and still they are incompletely hydrated cement particles, and they are going to even change the water cement ratio. That is the variation in water cement ratio across the matrix, which is not desirable from any point of view. Here, typically in the other microstructure image, you can see there's a paste aggregate interface. This is the aggregate, this is the paste, and this you can see this paste aggregate interface. Now this paste aggregate interface, this is actually the weakest microstructural component in concrete as such. And the important features which we observe in this zone are that one is, of course, we need to zoom it out further, and we can see whether these characteristic features are there in that portion which we are claiming to be like the paste aggregate interface or interfacial transition zone, or in simple terms, short term ITZ. So there are certain important microstructural features which are observed in this zone, and there one is you'll see a preferred orientation of large platey CH crystals in this zone. There will be lack of anhydrous cement particles in this zone, and this zone has a higher porosity as compared to the bulk paste which is available in the nearby vicinity. And there's an increased concentration of ettringite here. And how do we identify ettringite? Ettringite is sort of needle-like structures, as we have seen earlier also. Like these needle type of structures, they are ettringite. You can see here, these are ettringite, or these needle type of structures basically. So this is identified by these four, that there will be a preferred orientation of large platey CH crystals. There will be lack of anhydrous cement particles. The porosity will be higher than the bulk cement paste, and the concentration of ettringite will be more as compared to the other areas of the concrete matrix. Now, let's try to understand actually when we are doing this microstructure imaging, and we are saying that we have to observe the interfacial transition zone also. We have to look for this anhydrous, incompletely hydrated cement particles also. We have to look for calcium hydrates and CSH and adringite needles, etc. And we have to see the transition zone very clearly. So now there is a lot of complexity which is involved. Actually, what's happening is there are calcium silicate hydrate sheets, and we need to look for their interparticle spacing also. And this interparticle spacing is just 1 nanometer, that is 0.001 micrometer. Then we have to look for capillary voids also, which is 0.1 micrometer or 100 nanometer. We have to look for hexagonal crystals of calcium hydroxide also, which have a size of 1 micrometer. Then we have to look for entrained air bubbles also, the size for whom varies from 100 micrometer to 1 millimeter. And we have to look for entrapped air void, the size for which varies from 1 millimeter to 10 millimeter, in this range. So there's a huge variation. Now if you see, like if you have to see something in the microstructure which is of the size about 5 to 6 mm, at the same time we have to see something of the size of about 1 nanometer. And within one go, like we have to analyze these different magnification levels, and then we have to like sort of have a comprehensive analysis of the images at all those magnification level. Now, how difficult is that is can be understood by this. Like if this interparticle spacing between calcium silicate hydrate sheets, this is denoted by the size of humans. The size of human represents this interparticle spacing between CSS sheets. Then this final entrapped air void, that will be denoted by the size of Mars. So you can understand if somebody is asked to analyze or to carry out a study which will involve the study on a human being, at the same time which will involve a study of the complete Mars also, how difficult it becomes, and how difficult it becomes to relate this human being to the Mars diameter. So same is happening here. So a lot of magnification levels, the images needs to be taken out at a lot of magnification level. We also need to understand that if we are magnified at that level where we are just able to see at the level of say 1 micrometer, not below 1 micrometer, then we'll not be able to see the interparticle spacing between CSS sheets, etc. So it is very important at what magnification level we are taking the image, and at that magnification level, what is the phase or what is the characteristics which is likely to be observed or to be displayed, and then accordingly we have to take a decision. Okay. Similarly, like now people talk a lot about the mineral admixtures, different type of admixtures in concrete to improve the properties. So we can see easily now how this microstructure image helps us in taking a decision. Like here in this typical concrete matrix, what happened is mineral admixture was added. So you can see that when the mineral admixture was added, there's a dense hydrated cement paste. So all over you are seeing CSH gel. You're not seeing the platy crystals, or you're not seeing the adringite needles. So basically it is instilling a confidence that the mineral admixtures, they're creating a dense, highly impermeable hydrated cement paste and a strong paste aggregate interface with a distinctly lower amount of calcium hydrate crystals forming in this zone. And due to this, what will happen is the resultant concrete will acquire greater resistance to the penetration of external aggressive chemicals. And the size and volume of calcium hydrate crystals in this, when you will add the mineral admixtures, will become lower. And all these features, such as like matrix densification, refined paste aggregate interface, increased impermeability, and reduced porosity, now they can be recognized under scanning electron microscope. So this is the beauty, like if you are observing this like matrix densification, refined paste aggregate interface, or you're observing increased impermeability or reduced porosity, then that is giving an indication that yes, we do have a solid concrete now, which will behave better than the normal concrete after the addition of mineral admixtures. Now, sometimes it may happen that we may try to add some waste material or some alternative materials in the concrete. At that time also, we can see the effect of that alternative material in the concrete. Like here, we try to use waste rubber ash in the concrete. And when we use the waste rubber ash, then after replacing the fine aggregate by waste rubber ash and casting the concrete, then we studied the microstructure image of that. So here you can see it's very clear visible that this is the rubber ash particle, and this is a clearly visible gap between the rubber ash particle and this, you can say, between the rubber ash particle and these what you can say aggregates, etc. So there's a clear gap now between the rubber ash particle and the aggregate. That means this gap is basically a sort of interfacial transition zone, and that is going to cause the weakness in the concrete. And that means the strength which we are going to observe for the rubber ash concrete is going to be observed to be less than the normal concrete. And this is what we found at the when we actually tested the concrete. But the idea is that once we did the microstructure analysis, we were quite sure that this is going to happen, and that there was a sort of validation of the strength test also. Like here you can see at a greater magnification level, you can even see the cracks in the rubber ash particle themselves, and you can see this gap, or rather interfacial transition zone. Now if there is the rubber ash particle which otherwise is difficult to even see by naked eye, single rubber ash particle, you can see even up to crack in that, and you are able to see the gap in there also, which is sort of interfacial transition zone. Now this crack will not go in much in detail, but this crack in the rubber ash particle will also have its own effects on the cement matrix, or own effect on the behavior of the concrete. But the idea here is that it can be very well visualized, and similarly this gap can be very well visualized, and this gap is telling us indication that yes, the interfacial transition zone is not that perfect, so we need to be a little bit cautious, because the weakest zone of the concrete is not that good enough. So might be the strength is going to decrease. So you can see it from other angle, this gap is very clearly visible, and this is the rubber ash particle. Here you are seeing the gap in the matrix, cement matrix, or the crack in the cement matrix. So you're seeing interfacial transition zone, you are seeing the rubber ash particle, and you are seeing the cracks in this CSH portion of the concrete. So based on that, some inferences can be carried out about the strength and about the durability of the concrete. We are not going in that detail right now here, but the idea is that yes, they will have an implication. These features of the cracking and the gaps, etc., they are going to affect the strength and behavior of concrete. So you can see here, like at a bigger, another magnification level, when the rubber fiber, this time we used waste rubber fiber from tire. So when we use that, you can see it's a clearly, distinctly visible. This is the rubber fiber, and this is the cement paste gap between the rubber fiber. And there's a crack within the rubber fiber also. So this crack in the rubber fiber will have its own effect on the ductility properties of the concrete and on the flexural strength, etc. of the concrete. And this gap, cement paste gap, if you see the cement paste gap, that is slightly less if you compare it the same magnification levels. The cement paste gap is slightly less than that of rubber ash concrete. That means the properties will be slightly better than the rubber ash concrete. So if you have to use waste rubber tire, then we should use it in form of rubber fiber rather than in form of rubber ash. So you can see again here, like it's quite visible here, rubber fiber and this gap between the cement paste and rubber fiber. Again, it is clearly visible. This is the rubber fiber. This is the gap. So this gap is very clear gap. That means ITZ is still not that strong. And on this side, there's a cement paste. So all the features, they're quite distinct here. And based on these distinct features, we can infer, or we can predict what's going to be the behavior, what's going to be the effect of the cracking in the rubber fiber, what's going to be the effect of this gap between the rubber fiber and the cement paste, what's going to be the effect of this increased weakness in the interfacial transition zone, so how it is going to affect the overall behavior, overall strength of the concrete, and overall durability of the concrete. So all those aspects can be easily understood if we do a proper microstructure analysis. Like here, then we try to mix like sort of two waste material, rubber fiber as well as rubber ash in the concrete. So you can see this rubber ash particle is very well visible, and rubber fiber particle is also visible, and this gap is there at this end also, and the gap is at there. So rubber ash particle also is leading to a weak interfacial transition zone, and rubber fiber particle is also leading to weak interfacial transition zone. Of course, we can zoom out further and we can see that which one is causing more weakness in the interfacial transition zone, and the strength will reduce more due to which one of them. But the idea is you can clearly, distinctly visualize like the waste material or waste particles, which are very small size. You can distinctly see their effect on the overall, or you can predict their behavior due to the behavior of concrete due to replacement of these particles in the concrete. So here you can see easily, like this is the rubber ash particle, and this is the rubber fiber particle, and there's a gap between the rubber fiber particle and the rubber ash particle. So this gap is clearly visible, and of course its effect can be studied in detail. Again, from other angle, if you see, like this is the rubber fiber, and you can see this interfacial transition zone. This is the interfacial transition zone, and within this interfacial transition zone, the rubber ash particles are lost. So that's an interesting thing. There's a rubber fiber, there's a hydrated cement paste, a CSL gel, and between them there's interfacial transition zone. Just a minute. Hello. Uh-huh. Yeah, sorry for the interruption. Yeah. So basically, you can see very interestingly that even we can see that one waste material is lost into the interfacial transition zone between the other waste material and the cement matrix. And you can also see the internal cracking of the fibers here. And of course, this internal cracking has its own effect in the sense that if you will give some impact loading to the concrete, then this internal cracking of rubber fiber, first the rubber fiber will crack by itself. So it will sort of absorb the energy by cracking itself rather than the cracking of this cement matrix. So it will, in a sense, it will increase the impact resistance capacity of the concrete. And this is what you can observe also, like if you use waste rubber fiber in the concrete and if you observe the impact resistance, you'll find out a higher impact resistance. Now that is otherwise difficult to justify and difficult to predict by the conventional test. But based on that, you can just correlate the effect of the microstructure on that. Here you can see like there's a aggregate here and there's a cement paste here, and these rubber ash particles, they are lost here. So very clearly visible lost rubber ash particles. You can see even the micro cracks here and the micro cracks within the rubber ash particles. So they will also have their own role to play. They will also little bit of support in the higher impact resistance of the concrete. So the idea is, but you have to identify, you have to see the magnification levels, and at those magnification levels, like, am I audible? There's some disturbance, I think. There's some disturbance. So you are able to observe different type of images at different magnification level. Like, of course, we are zooming out at the same point, but here here it is the magnification level is 5000x. Here it is 20,000x. So here it is 1000x. Here it is 500x. So depending on the magnification level, we are observing different features here. Again, here, like this is clearly visible. This aggregate. This is the rubber ash particle, and this is the rubber fiber. And you can see this interfacial transition zone very clearly. Aggregate, this ITZ layer, very clear ITZ layer. This is a gel cloud type of a structure. These platy crystals, calcium hydroxide. Here, very clearly visible rubber fiber, ash particles, ITZ layer. Here the cement paste, rubber ash here, and this rubber fiber. And so all these features, they can be observed in the scanning electron microscope. Even you can like see what's the effect of the temperature. Like you don't need to go even for scanning electron microscope because that's a costly equipment, like which costs more than 1 crore rupees. But you can use the normal optical microscopes also, which cost less. So here, like through the optical microscope, the images were taken and we tried to see what is the effect of temperature on this rubberized concrete. So here you can see that it's just a 90x magnification level. And even at 90x magnification level through a normal optical microscope, which otherwise is available in most of the laboratories, you can even at 90x, you can easily see this gap between cement paste and rubber fiber, very clearly visible gap between cement paste and rubber fiber. So always you need not go for that high level. Now then we increase this temperature slightly of rubberized concrete, and we try to study the images at different temperatures. Like here, when it was subjected to 450 degrees centigrade temperature. So you can see here, there's a gap now between the cement paste and rubber fiber. And when we went to 600 degrees centigrade temperature, this gap increased. Again, this is the rubber fiber. And even there is a cracking in the, within the rubber fiber also the gap is increasing. The internal fibers, there is internal cracking also within the rubber fiber, and the gap between the rubber fiber and the cement matrix is also increasing at 600 degrees centigrade temperature. So you can see at normal temperature, this was the gap basically, which has increased now. And when we are seeing it at 600, we are talking about this part. So at normal temperature, it was looking like this, but at 600 degrees centigrade, at the same magnification level, size is increased. So within rubber fiber also the crack size is increased when the concrete has been subjected to higher temperature. So you can see like at 750 degrees centigrade, now this is clearly visible. Now the rubber fiber is sort of coming out of the cement matrix and it's breaking bond almost clearly from the cement matrix. So this is another observation which can be seen. And even at like, you can see the micro cracks, surface cracks also, which can be observed through these things. Now, it's not only about use of waste material, etc., but like say we can see at the level of material also. Like people often talk about this fly ash, and we know that fly ash is a pozzolanic material, which in the presence of cement reacts in the presence of water and cement forms calcium silicate hydrates. And nowadays, earlier days, ordinary Portland cement was used. Nowadays, most of the time you get Portland Pozzolana cement, only PPC cement, which comprises a good portion of fly ash. So why this fly ash is improving the properties of concrete? Now that is very well understood by the microstructure. So you can see there are two microstructure images at the same magnification level, that is of 2500x. So same magnification level, 2500x. And you can see if you compare the cement particles and the fly ash particles, in comparison to the cement particles, the fly ash particles, they are quite smooth and spherical. So that is smooth and spherical shape of this fly ash particle tells us that yes, now the hydration reactions are going to be more because the particles are spherical. So there is more surface area which will be available for this. So more surface area will mean more reactions, and more reactions will mean that greater strength. So this is what can be observed here. Even like say we try to replace the fine aggregate by the granite waste. So we saw their microstructure image. So it is more or less similar type of microstructure image which we are seeing here. So it's always advisable to first compare the microstructure images. If you're replacing the waste fine aggregate by certain material, then we can compare. Even if you are trying to put two admixtures, then we can compare their microstructure images, and we can see, we can at least predict that which material is going to behave properly. This material is going to give us good strength. So like here you can see microstructure of granite waste concrete. When it was put in the concrete, then this ITZ is clearly visible here. These voids here, they are clearly visible. This very clearly visible ITZ here. And then these are cracks. And you can see these voids are visible here. ITZ, again these voids and this ITZ. So these features, they can be easily identified by going through this scanning electron microscopy. Another advanced microscopy technique is TEM, and you can see that the silica fume particles, if they're further zoomed out under TEM, and this you can see this image that this is denoting just 0.5 micrometer. Even at that zoom level, these particles are looking as smooth and as spherical. So that gives us confidence that yes, these particles, silica fume particles, they're quite smooth and spherical. And that is one of the reasons why silica fume is used for high performance concrete. And those who have been working in the concrete technology, they know that in Indian standard 10262 recent version, they have defined separate mixed design procedure for the high strength concrete. And while defining the mixed design procedure for the high strength concrete, they have suggested the use of silica fume. The reason for the use of silica fume is this only, because it has a quite smooth and spherical particle and small size. So it gives a very large surface area for the hydration reaction, which means a large amount of hydrated cement paste or large amount of CSH gel, which in turn means good strength. Another technique is called X-ray diffraction. Here we use that scanning electron microscopy. Basically, we use sort of pellet samples, but in XRD technique, we use powdered samples. So we just crush the concrete or take a powder and take a sort of representative sample. So if we do this XRD, then each crystal, it's based on the principle that each crystal has a unique pattern and it reflects different intensity of light at different angles. And this XRD analysis identifies basically the minerals present in sample using the observed intensity patterns. So here typically this XRD is shown here. So this is X-ray beam which is striking the sample, and these are sort of diffracted beams. And this is the detector which is receiving the signals and which is detecting at what angle this is getting reflected. And based on those angles, you can identify the minerals which are present. And of course, standard databases are there, and you can use those standard databases. And corresponding to each angle, there might be 100 type of minerals which can be there. But we have to identify actually which mineral is likely to be there in our concrete matrix. So we just identify that. So calcite is observed at these angles. 100, 34, 29, 2 degree. It is 2 theta basically, 2 theta angle. So calcite is observed at that. Calcium oxide is observed at these angles. Calcium hydroxide at these angles, and so on and so forth. So there are different you can identify calcite, calcium oxide, calcium hydroxide, magnesite, dolomite, brucite, quartzite, gipsite, barite, diaspore, triclinic halite, because halite has also different phases, 2-3 different type of phases. So belite also, beta phase of belite, and aluminate also. So this is just a representative table. Actually, you can have hundreds of more minerals there. And this is a typical XRD pattern of halite, where this is even in halite, it is not just one type of halite. People think that the C3S is there, so only C3S presence is important. They just talk about the total presence of C3S. But what is important is how much, in which form it is there. So whether it is present in rhombohedral form, single sharp peak, or it is present in monoclinic form, 2 sharp peaks, or it is present in triclinic form, multiple sharp peaks, because each form will also have different effect on the overall cement chemistry and overall concrete matrix. Now this monoclinic and triclinic forms, basically they are predominant in clinkers, and rhombohedral form is rare. So the idea here is that the peak patterns for different mineral phases is quite unique. For other type of cement composites also, look for belite alpha phase will look like this, belite beta phase will look like this, C3A XRD pattern will be like this, C4A AF will be like this. Here you can see there are 2 peaks. One peak will be observed at this angle, another peak is observed at this angle. So it is not necessary that only one peak will be observed corresponding to one composite or one mineral. There can be multiple peaks. Like for beta C2S, so many peaks. So C3A also multiple peaks. So we can identify, it's not that there will be only one peak, there can be multiple peaks also for each mineral. Here typically this is an analysis of XRD pattern for fly ash, which was done in our laboratory only. So here you can see easily that this is the most dominant phase, quartz, and then this quartz is present at other angles also. So quartz is there, and then mullite is there. 2 is mullite. So along with quartz, there is mullite. Of course, quartz is also predominantly available at this angle, but then it is present at different angles also. Similarly, mullite is also predominantly available at this angle, you can say, but then this angle, but then it is present at different angles also. So minerals present can be understood by recognizing the peak patterns of known minerals, and based on initial peak, here the quartz is identified because this is quite high peak, and this is basically a relative intensity count. Next time it may be 3500, doesn't matter, but it is relative count of 1:2. It's not, this is not important. What is important, absolute values are not important. What is important is relative intensity. So that should be understood. So minerals present can be understood by recognizing the peak patterns of known minerals. And based on initial peak, quartz is like identified here. And after removing pattern of quartz, once you remove that, then you can identify the mullite. So this is the manner in which you need to do the XRD analysis. Like here, this is mineral identification in other samples like quartz, elbite, microcline here. So you are able to see the quartz, you are able to see elbite, and you are able to see microcline also. Here, like this is about the fine aggregate, but if you talk about the granite waste, then along with the quartz, elbite, microcline, there's orthoclase also and anorthoclase also. So different types of like minerals are present in different samples. And when we compare, like here, if we compare this fine aggregate to granite waste, we are replacing the granite waste, replacing the fine aggregate by granite waste. So what benefit we are getting from this XRD images is that we very well know in the beginning only that once we'll replace the fine aggregate by the granite waste, then basically two more types of minerals will be there, orthoclase and anorthoclase, which are not there in the fine aggregate, conventional natural fine aggregate. That means whatever effect we will be observing, that effect will be basically effect of orthoclase and anorthoclase. That is one. Another is we have to see also the relative intensity. So the relative intensity of quartz is like say less here as compared to this. So another, though quartz, elbite and microcline are present in both, but the relative intensities are also changing. So based on that relative intensity also we can predict the behavior. Like here, like this was at the level of aggregate or like the level of ingredients, raw material. Here this is like level of concrete. So here, like on left side you are seeing the XRD image of a XRD pattern of a traditional concrete. So here you can see we are observing basically silica, CSH, portlandite, ettringite, dolomite, calcite, alumina, sodium oxide, potassium oxide, magnesium oxide. But for this 40% ceramic waste, when we replace 40% this fine aggregate by the 40% ceramic waste in the concrete, then the minerals which you observe are the same again: silica, CSH, portlandite, ettringite, dolomite, calcite, alumina, sodium oxide, potassium oxide, magnesium oxide. So that means that no additional chemical is formed. That means more or less the behavior will be same. So it might not be beneficial also, but it's not going to be detrimental also. Of course, relatively certain relative intensities are changing. So we need to take into account that effect. So we can see that the same minerals are present in both type of concrete with the change in peak intensity when we use the ceramic waste. So it is showing that as such ceramic addition is not forming new minerals or no new chemical reactions are there. Only thing is the relative intensities are changing. Like here, like then we replaced by 20% also and 60% also. So every time we are getting more or less same type of minerals or same type of chemical composition. Only thing is there is a change in the relative composition. We can also do the durability assessment, like alkali silica reaction is one of the common reactions which decreases the durability of concrete. Now this probability of alkali silica reaction, it is basically a reflection of the intrinsic crystallinity of the silica form. So we know that the silica is as such present in two forms, amorphous form and crystalline form. Now this crystalline form is detrimental in reference to the alkali silica reaction. Alkali silica reaction is basically due to the crystalline form of the silica which is present in the silica. So as such the total amount of silica is not detrimental to the concrete from the perspective of the alkali silica reaction, but the crystalline form of silica is detrimental. Now the crystallinity index of silica by XRD technique here which has been done, it is based on the measurement of relative heights of peaks which were occurring between the 2 theta angle of 67 degree to 68 degree. And of course, the relationship of mortar bar expansion with crystallinity index of various form of silica is also compared with help of autoclave expansion chart. So basically, we can find out the crystallinity index, and this crystallinity index that will give us indication of the alkali silica reaction, how much alkali silica reaction is going to take place. Similarly, we can identify the sulfate minerals. As such, generally we say or we consider all sulfate minerals together. But actually the sulfate minerals, we need to understand that they are present in different forms. And each form has its unique role in the concrete behavior. So we need to understand that, like if it is present in the form of ettringite, like ettringite is observed here, it is present in form of thaumasite, or it is present in form of monocalcium sulfur, calcium monosulfate hydrate, or it is present in form of gypsum, or it is present in form of bohemite. Now every type of sulfate mineral will have a completely different role to play in the cement chemistry or concrete matrix. So this otherwise is not possible to do by normal analysis, but through this XRD we can identify these different types of minerals: attringite, thaumasite, calcium monosulfate hydride, gypsum, bohemite. And these are like attringite is basically C3S, 3CS31H, thaumasite is CS, CSU3CS, gypsum is CS2H. So all are like different chemical composition. Only thing is they all are sulfate mineral. So by XRD, we can easily identify that which type of composition is there. Then we can go for IR spectroscopy also. This is also a very recent tool, and those are comparatively new in cement and concrete, but this is gaining much importance with the advent of user-friendly equipment and continuing research on identification and characterization of reaction products, new minerals, etc. Now, this technique, this identifies the bonds based on the energy absorption. So the energy is absorbed at what level, and based on that, so it identifies the bonds, and the bonds are not directly the sort of concrete bonds. We have to identify that which type of bond is there. Only thing is, like here we can see the S is telling us that it is strong bond, M is telling us this. So S means a strong bond, M means medium bond, W means weak bond, V means variable bond, N means narrow bond. And at what wave number we are observing, what wave number the energy is absorbed, corresponding to that wave number we can see that what is the type of bond which we observe here. And that bond can be related to the minerals which are present in the concrete. So like here there are typical results obtained in IR spectroscopy for fly ash. Its IR spectroscopy will look like this. So you'll observe some peaks here, some peak here, and some peak here. Similarly here, like slag also you can see certain peaks. So based on that characteristic functional group you can identify it. Like here also, like gypsum, you are identifying at different levels. So you can identify such type of minerals at different levels. Okay, so like here you are identifying the band at 1140 also, and sort of this is 1140, then 668 also somewhere here, and 602 also. You can also estimate the dolomite content basically, and this is very important because like when people are trying to look for the clinker for the cement industry, then it is very important to know the dolomite, how much dolomite is present there. So the infrared spectra of calcite and dolomite that is typically characterized by band at 711 and 722 wave number respectively. And these bands typically they are unperturbed and sharp with varying intensity depending on the concentration of these minerals. So like here you can see, like if 20% dolomite is there, it looks like this. 30% dolomite is there, it looks like this. 40% dolomite looks like this. So how much dolomite is present, based on that these characteristic peaks are going to change. So you can quantify the minerals basically. So this is typical characterization of clinker, which is containing about 20% dolomite, here which is containing about 30% of dolomite, here which is containing about 40% of dolomite. So just by IR spectroscopy, you can estimate the dolomite content very easily, which otherwise is a difficult task. And based on that dolomite content, you can decide whether you are going to use that limestone in your cement industry as a clinker or not. Like you can identify like, so each sort of mineral has its own characteristic phase, and that corresponding to that characteristic phase, there are certain wave numbers associated. Like so says for C3S also. So you can observe it in triclinic phase, monoclinic phase, and oxidizing phase. So if you are seeing it in triclinic phase, you'll observe at these wave numbers. Its monoclinic phase will be observed at these wave numbers. Oxidizing phase will be observed at these wave numbers. Similarly, belite, like elite is in 3 phases. So belite can be observed in 3 phases. So these are different wave numbers at which this is observed. Similarly, C3A also, like at different wave numbers it can be observed. So this is how like sort of you can identify the cement composites, not only the cement composites, you can identify the phase in which they are present in the concrete. So again, like if you see like through IR spectroscopy, if you compare, like as you were discussing about the sulfates, different types of sulfates. So there is a considerable difference between the spectra of like monosulfate and ettringite, etc. So that is quite that can be well differentiated by the use of this. And the various forms of calcium sulfate, they can be clearly identified by IR spectroscopy. So the useful IR range for their characterization is like 1000 to 1300, 1550 to 1750, 31 to 700 wave number. So basically you can identify different types of sulfates using IR spectroscopy. Like here, this is FTIR of traditional concrete and FTIR of ceramic waste concrete, and this is the figure graph which we got. So here, like we observed at these wave numbers, and if you see these wave numbers, they are corresponding to these functional bonds OH, CO, SiO, SiO, Si, So, CS2, CS3, and these functional bonds, now it depends on us now to which mineral we are going to assign them, because they may be assigned to thousands of other type of minerals, but we know that in the concrete mostly it can be assigned to calcium hydroxide. Here it will be assigned to calcium carbonate. It can be assigned to CSH, SiO2, SO4, methyl and methylene. So by this wave number, first we will identify the functional bond to which it is associated, and through the functional bond we will assign to certain mineral which is likely to be present in the concrete matrix. So again here, like this is FTIR spectra for control concrete, FTIR spectra which is containing 20% of ceramic waste, FTIR spectra which is containing 40% of ceramic waste, FTIR spectra which is containing about 60% of ceramic waste. Another important microstructure technique is NMR technique, and there are certain advantages. Like here, you can see how much CSH is formed and in which phase it is formed. So CSH is the dominant strength forming phase in Portland cement paste, and determination of its structure and behavior has been a central topic of cement science for many decades, because we want to see how much CSH has been formed. Not only that, in which phase it is there, how much hydration reaction has taken place. So NMR spectroscopy can be used. Like here, you can see the CS ratio. So C by S ratio is changing from 0.1 to 0.79, 0.88. So it depends, like the C by S ratio is changing. That means more and more hydration reaction is taking place. So depending on at which level the CS ratio we are getting, that will give us an indication of how much hydration reaction has taken place. Like here, this is the analysis of results on concrete. So this was the like sort of traditional concrete, and this was concrete which is containing 40% ceramic waste. So in the traditional concrete, we can see that there is a ratio Q1 by Q2. Q1 is the first phase, Q2 is the second phase. So if Q2 is more, that means second phase is more, that means more hydration reaction has taken place. So here Q1 by Q2 is 0.934, but here it is 0.903. That means Q2 is more here, that means more reaction has taken place, that means this is better. Even if you can directly calculate degree of hydration, which is coming out 48% here only after some calculations, but this is coming out to be 73.4% here. So the degree of hydration also is more. We can even calculate the bond length. Also the chain length of the bond. Here it is 4.13 only, but here it is 4.21. That means the chain length of the bond is also more here. So this is how we can compare two different types of concretes using this sort of NMR spectroscopy. And another very latest technique is lateral force microscopy, and it's useful for observing the surface structure of insulating materials by physicists. And it's a very delicate technique, and because the needle is very, very sensitive. And of course, in the field of cement and concrete research, they are now being used for observing the crystal structure and surface structure of clinker minerals, hydrates, and absorbed layers of organic admixture on the surface of cement particle. And you can see here, like we have to prepare very small concrete sample, and we have to polish it very carefully. And you can see the surface topography here, like the two types of concrete are compared here. One is the traditional concrete. Another is second concrete, which is containing say 40% ceramic waste. And the needle taps over this concrete actually, and it measures, or you can say it stores the profile. So you can see the profile on this both sides. So here it is like sort of staggered profile, and here it is sort of smooth profile. Also, if you see the image here, like you can see some bright spots. So these bright spots are unhydrated cement particles, and you can see some pores also. But if you see this type of concrete, so there are no bright particles and no pores. So if you compare these two type of concrete, you can easily say that the left side concrete has more unhydrated cement particle and more pores, but the right hand side concrete is better. So this is the manner in which you can use that. And you can even see this 2D and 3D phase imaging also. So like if you see the 2D image of the two concretes, here it is showing the non-homogeneous phase, but here you are seeing quite homogeneous phase. If you go in 3D phase, 3D imaging, then there's a high variation in distribution of phases, and there's relatively smooth distribution of phases. So this is what can be done through lateral force microscopy also. So these were some of the techniques of microstructure of concrete, which we have discussed today. If we summarize, we can say that the techniques discussed above are useful for analysis and prediction of many material-related issues, such as resolving the durability issues which are related to the mechanisms of reaction, for determining the parameters that influence reaction kinetics of processes that affect material properties and service life of building elements, for developing and characterizing new materials for the durable structures, and for establishing reasons for structural failures and conducting related forensic investigation, and for providing a basis for the development of relevant standards and methods for advancing aspects of objective-based course. So these are different uses of microstructure images, microstructure analysis technique. I think now we can have some discussion. Dr. Parikh? Dr. Parikh, am I audible?
Yes, sir. You're audible.
Yeah, so I think we can have some discussion now.
Yes, sir. I think the participant, if you have any questions or any query, you can drop in chat box, so we can discuss with sir. You may unmute yourself. So we'll wait for a couple of few minutes. As participant may write in chat box.
Sure. I'm with
Okay. Sir, there is a one query is there. Can you determine the quantum of cementitious paste through microscopic analysis? I mean,
yes,
is there any
that can be done cementitious paste that can be done through certain chemical analysis, not through microstructure images, but yes, through chemical analysis we can find out that.
Okay.
In fact, there is a new standard code also for that. So you need to do some chemical test.
And sir, how it is correlated with basic calculation? I mean, based on equation. I mean, there is a CPV that we normally find out based on the volume based.
Actually, like the one which you'll do from the chemical analysis, that is quite different. Like you need to do some titrations and you'll get a cement content. But that is not very accurate. So I cannot comment how it is directly related because that's an approximate method actually. So there also you need to do it multiple times.
Okay. And one more thing, sir. The pervious concrete without coarse aggregate but with fiber. So how could be the interface behavior between based on there is a.
So you are saying pervious concrete with fiber.
Yes, sir. I mean.
Okay. Now it depends actually which type of fiber you are using. Like typically we have shown here the waste rubber fiber. But say there are 10 type of rubber fiber, each will have a different effect on the microstructure. In pervious concrete, essentially what we are going to do is we are reducing like sort of fine aggregate in the concrete. That is what we are doing. So it depends like how much waste rubber fiber you are using, which type of mixed design you are using. But directly it cannot be said that what is its effect, because perviousness is related to the mixed design at other level. Like we are creating sort of voids at a larger level. But the ITZ is at a smaller level. So at that level, how it is going to work, that is quite different. Because they both have different magnification levels.
So it might be thing is that when we are using fiber, so if we have a fine aggregate, then in that case we might have a proper interface. I mean, might be have a good strength.
Yes, yes, because mostly fibers they are used as a for replacement of fine aggregate mostly. So, like if we are going for coarse aggregate, then along with that, using fiber, that might create mostly some complexities.
Okay. Okay, there is a one, I think, small query might be there.
Yeah.
So it is asking about use of recycle aggregate.
Yes, recycled
So
aggregate
how?
can be used in the concrete. Only thing is recycled aggregate when we are using them, they do have some mortar which is adhered to them. Now that adherence of mortar is a big problem because that mortar is sort of dry mortar. So it absorbs a lot of water. So it changes the water cement ratio. So, or you can say it decreases the workability. So to improve the workability, you have to add more water and then it decreases the strength. But nowadays, like sort of techniques are available, like where you can remove the mortar. One is like by some mechanical method or by some chemical method or by heat treatment method. But the best method is like you can pre-soak the aggregates in the water for 24 hours before use. So that whatever water is to be absorbed by like sort of mortar, it will already absorb that water. So it will not change the water cement ratio. Otherwise, it gives more or less good strength. And people have made multi-stories also, like in other countries, using the recycled concrete aggregate.
Okay, sir.
Yeah.
Thank you once again, sir, from the
Okay.
our side. It is from GC
Yeah. Thank
Dahod.
you, Dr. Parikh.
I
Thank
think
you.
about in most of the lectures we are talking about strain aspect. So thank you for covering this microscopic point of view. I think
Yeah.
through your lecture, the participant may get interested now behind the microscopic structure behind your microscopic structure.
Yeah.
So
Okay.
thank you very much, sir.
Thank you, Dr. Parikh. Thank you. Thank you all.
I think a participant we may leave. I think sir have a few works. That's why done early. So we'll meet after a few break. Okay.